Okay. All right, so we ended the last lecture in sort of the middle, second law of thermodynamics. So I was kind of rushing this towards the end, so I'm going to kind of go a little bit overview of what we did before we ended last time, just to get you back into the same space where we were, okay? So we're going to be talking about the second law of thermodynamics, and what we learned was that when you think about the second law, it really kind of starts with this understanding that heat will not flow spontaneously from a warm body, from a cold body into a warmer body, right? So there's a directionality that heat flows, which has nothing to do with the first law in the sense that both processes are allowed by the first law, but we know that one process is impossible and the other one proceeds spontaneously. So for example, if I had these two boxes where one side of the box had a gas that was at 400, the other side had a gas at 200, and there was a diathermal boundary between them, then we know spontaneously that would go to, these were two identical amounts of the same gas, it would go to both sides being 300 and 300. You could still satisfy the first law and have this side get cooler and this side get hotter and go this direction, but that is a process that never happens, right? So the statement of the second law, as Clausius gave it, was that no process is possible whose sole result is the transfer of heat from a colder body into a hotter body. So what was needed was some kind of quantitative measure of this statement, right? Some kind of thermodynamic property that would recover this behavior so that we can have a way of sort of keep putting this into the equations, okay? And this is something that Clausius discovered by a careful review of the Carno engine cycle, which we talked about last time. So let me just quickly go through how that worked. So Carno was interested in trying to find out about efficiencies of heat engines. And so he was looking at engine cycles where you bring the system through a thermodynamic cycle and you come back to the same point, the same thermodynamic equilibrium state, and in that process, in that cycle, you get work out of the system. And that process required you to use a hot reservoir and a cold reservoir, and that flow of heat from the hot reservoir to the cold reservoir is what you exploited in order to get work out of the system. So you're taking heat out of the hot reservoir and you're converting some of that into work as it flows into the cold reservoir. All right? So that's the picture that it had, and the way you would implement such an engine, again, was imagine you have like a simple piston cylinder apparatus and you have it connected to the hot reservoir. So it's at the hot reservoir temperature, and we have an isothermal expansion. Remember, we worked through the equations for the isothermal expansion. We have an isothermal expansion where we pull heat from the hot reservoir into the gas, and the gas expands, and we get work out of the gas during that particular step. Then we disconnect it from the hot reservoir, and we allow it to continue to expand, getting work out of the system. But now, because it's adiabatic, there is no heat flow into this. So as it expands, the system is doing work, but it's losing energy, so the temperature is dropping, right? So we do that until it reaches the temperature of the cold reservoir. And then the next step is we connect it to the cold reservoir, and we start compressing it. So now we're putting work into the system, and as we put work into the system, it's also going to be dumping heat into the cold reservoir, and we're going to do that and until we reach a certain volume, and then we're going to disconnect it, and then we're going to apply more work and adiabatically compress it when we go from the cold reservoir temperature back to the hot reservoir temperature, and then we're going to repeat the cycle. And in that process, we've got work out in the first two expansion steps, isothermal and adiabatic, and we put work in the compression steps, which was isothermal adiabatic, but there's a net work that we get out, and that is what we're after in terms of the efficiency of this engine, okay? So that's the actual process. If we plotted that in a PV diagram, And remember, this is all done reversibly, so we can plot lines here to show the state of the system throughout this process. We have the isothermal expansion step, the adiabatic expansion step, the area under that is the work. Then we have the compression steps, we have the isothermal compression and the adiabatic compression, the area under that is the work that we put in, whereas the area was the work we got out for the first two steps. And the area inside this curve is the net work, right? The negative of the net work, right? So the area under the curve is the negative of the work that you get out. So the area inside this is the negative of the net work. And you can work out that works out to be this expression here, all right? So that's how the Carno engine cycle works. It's done reversibly through this cycle. And this is what Sadie Carnot had worked out. He'd worked out the efficiencies. And again, it was a very simple argument, just using the first law, just adding up the heat flow in, the work that goes out, and the heat flow that goes down. All of that has to add up to 0. So the efficiency of the engine was simply the work that we got out divided by the heat flow that came from the hot reservoir. So we have a negative sign here, so this is a positive quantity. And then we rearrange this into this expression here with this becomes this, and then a little rearranging, we get the efficiency as just the 1 plus the ratio of the heat flow into the cold reservoir, which is a negative number, over the heat flow coming from the hot reservoir, which is a positive number. So this is 1 minus a number here, and this number goes between 0 and 1, okay? But it never reaches 1 because that would be 100% efficiency, so it's always going to be less than 1. All right, any questions up to this point? All right. So one of the things we talked about then was that you could take a heat engine and you can run it backwards. So you can just do the cycle instead of the expansion, expansion, compression, compression. You can do compression, compression, expansion, expansion, and do that cycle backwards. And you would create what's called a heat pump. So it would actually do the job of you putting net work into that system, and it would take heat from the cold reservoir and move it into the hot reservoir. But it takes work to do that, right? That's not going to happen spontaneously. You would have to do work to do that. So running it one way forward is the heat engine where you get work out. Running it backwards is the heat pump. Now, what Clausius realized was, Sadie Carnot realized was that a heat pump and a heat engine running between the same heat reservoir and cold reservoir, hot reservoir and cold reservoir, would have to have exactly the same efficiencies regardless of what was in it. And the reason is because if you had different efficiencies running between the same two reservoirs, you could imagine you could combine a heat pump and a heat engine together in such a way that you create a device that violates the second law statement, allowing heat to flow from a cold body to a hot body, from a cold body to a hot body spontaneously. And so the way this works is, imagine you had like just a heat efficiency of 1/4. So that means that you would pull 4 joules from the hot reservoir, 3 joules would go into the cold reservoir, and 1 joule would come out as work. You would feed that into the heat pump, where 1 joule would be used to take 4 joules from the cold reservoir to put 5 joules into the hot reservoir, and that pump has an efficiency of 1/5. If those were different like that, then combined they would give you a device that would take 1 joule from the cold and put it into the hot without any work. And that's obviously not going to happen, right? That's going to make it be a spontaneous process that would violate the second law statement. So the only way you can prevent that was to insist that all heat pumps and heat engines operating between the same hot and cold reservoir have to have the same efficiency, regardless of what's inside them. All right? So that means then that we could use the ideal gas, doesn't matter what's inside it, to actually work out how that depends on just those temperatures of those two reservoirs. And so we worked through these derivations earlier, but just again to refresh your mind, this is what we found for the adiabatic steps. So we had these two integrals during the adiabatic steps, and we can combine those guys for the two steps, the adiabatic compression and the expansion, and we can get this expression here for relating the volumes of the 4 steps, beginning and end of the 4 steps of the process here. And then for the isothermal steps, then we derived this expression for isothermal expansion and compression. So if I take the ratio of these guys, which is what we had here in the earlier expression for the engine efficiency, if I take this ratio from the isothermal expansions and I calculate that ratio and then use what I get from the adiabatic expansion and compression, I can turn this QH over QC into minus TC over TH and then substitute it back in, and I get the engine efficiency entirely in terms of the hot reservoir, cold reservoir temperatures. All right? And you can see again, makes sense that if they have exactly the same temperature, then you have 1 minus 1, you have no efficiency whatsoever. But to get perfectly, 100% efficiency, you'd have to have, your cold reservoir at 0 Kelvin, which is not going to happen, or you'd have to have your hot temperature at infinite temperature, which is also not going to happen because the molecules can only move at the speed of light at the maximum, right? So you can never reach an infinite temperature here. So that is the Carnot engine efficiency just in terms of the temperature of the hot and cold reservoir. Very simple expression. You guys see how that, we went through this. So again, we're just doing everything we did in the last lecture here, just we're going back over this again so you can see this. Any questions on this? Maybe you saw this, those of you who took thermo in chemie, did you do the Carnot engine? All right, perfect, great. Okay. It's not so bad. Now, what Clausius realized when he was reviewing all of this was that in this cycle, he found, if you go back to the previous slide, you saw that QH over QC was equal to minus TC over TH. So you can rearrange that expression to look like this. And then for the cycle, you could rewrite it like this. So you can say that the heat flow during the reversible expansion divided by the temperature during the reversible expansion plus the heat flow during the reversible compression when it's connected to the cold reservoir divided by the temperature in which that occurred adds up to 0 in this cyclic process. So what Clausius realized was that any cyclic process that you can imagine, if you took the pressure volume diagram and you drew the lines that were isotherms and you drew the lines that were adiabats and you just do every possible adiabat isotherm line, that any cyclic process you could draw as some kind of circle, no matter what the shape is, you can always decompose it into a little bit of an adiabat, isotherm, adiabat, isotherm, adiabat, isotherm as you work your way around, so that no matter how you went around that cyclic process in a reversible way, the sum of all those isotherms is going, the heat flows during the isotherms divided by the temperature is going to add up to 0. So what he realized was that in a continuous limit here, you have this integral that dq reversible over t at each point where the heat is being transferred has to add up to 0. And that property of a function that comes back to its original value at the end of a thermodynamic process is the definition of what we know would be true for a state function. So Clausius had discovered a quantitative measure of a state function that was related to the second law, which he called the entropy. So the differential form is here, that the differential change in the entropy, so we use the symbol S for the entropy, and during a reversible process, it's the reversible heat flow divided by the temperature at the boundary at which that occurs. Okay. Any questions there? Okay. So this was a big step. This gave us an equation now that allowed us to be able to quantify into the equations, this second law statement that heat doesn't spontaneously flow from cold to hot bodies. Okay. So let's take a look with Clausius' definition. We can go back and look at all the thermodynamic processes that we looked at before, and now we can calculate what was the entropy change during each of those types of processes. And so for the reversible ones, it's very simple. We just need to know what the heat flow during that reversible process. So obviously, any reversible process where the heat flow was 0 has to be a delta S of 0, right? It's what we call an isentropic process. So when the entropy remains constant, it's, we talked about, isobaric, isothermal. If the entropy stays constant, it's an isentropic process, all right? Another process is when you're doing heating, and we know that if you're doing heating isothermally, then you know that the heat flow is just the heat flow that you measure going in divided by the temperature of the boundary. The temperature is constant during isothermal process, so the T slides out of the integral. It's just the integral of the heat flow reversibly. So the change in the entropy during any isothermal process, reversible isothermal process, is just Q over T. So that's pretty straightforward too, right? If we took the case of the ideal gas, where we worked out the heat flow during that isothermal process, then we calculated an expression for Q. If we just divide it by T, this is what you would get for the entropy change. So remember that isothermal expansion, we worked out the heat flow during that process. The entropy change is just Q divided by T in that case. Okay, so the entropy increases during an expansion isothermally, and it decreases during that expansion, during recompression. All right. Okay. During a phase transition, so when you go from, say, liquid to gas, or solid to gas, or solid to liquid, all of those phase transitions, we know that the heat flow under constant pressure is just the enthalpy change for that process. So in a constant pressure process, we can say that the entropy for each of these transitions, fusion, sublimation, vaporization, is just delta H over the temperature in which that process occurs. So you can see we're just working through the list of easy processes where we can calculate the entropy change during those processes, just using the definition that Clausius had discovered for entropy. Any questions here? Now, let's talk about irreversible processes. Remember that state functions, and entropy is a state function, are independent of the path. So if I have state A at equilibrium and state B at equilibrium, and I connect them with a reversible process, or I connect them with an irreversible process, the difference in the state functions in A and B, whether they were connected with reversible or irreversible processes, is the same, right? Because it doesn't depend on the history for a state function. So if I was doing a reversible expansion, and I know that the area under that curve is the negative of the work, versus an irreversible expansion between states 1 and state 2, you can see that in these two processes, that obviously the work is not going to be the same in the irreversible versus the reversible. We talked about the differences in work flow during reversible and irreversible processes. But of course, states 1 and 2, the state functions describing those equilibrium states, the differences in those state functions are identical, right? So if you thought about the internal energy, then you know that if I'm connecting state 1 and state 2, the internal energy, whether it's this process or this process, the change in the internal energy has to be the same, because it's a state function. But you see that the work involved is different. And obviously, if delta U is the heat flow plus the work, then the irreversible heat plus the irreversible work has to add up for the same two states to the reversible work and heat that would have gone in this case, in this case, right? So in other words, the heat and work in this case has to add up to the heat and work in this case, although the heat and work individually are different, right? There is less work over here than there is over here, and obviously, if delta U is going to be the same, there's going to be less heat flow over here than there is over there, in order to keep delta U the same. So we know that the irreversible work, the magnitude of the irreversible work is less than the reversible work, and obviously the magnitude of the irreversible heat is less than the reversible heat. Okay. So if we take the signs into account, that means that for this process here, the irreversible heat flow has to be less than the reversible heat flow. You follow that argument, okay? So we have delta U has to stay the same. So if the work is bigger over here, then the heat has to be bigger over here also, right? The magnitude of that. So that means that for the reversible process, we know that Q reversible is greater than Q irreversible. And if we divide both of those by temperature, then we know then that Q reversible over temperature is greater than Q irreversible over temperature. And Q reversible over temperature is the entropy. So I can replace this side of the inequality with the change in the entropy. And now we see that for any irreversible process, the change in the entropy is always greater than the heat flow over the temperature. So now we have this inequality, but we know that it has to be always greater than that. Okay? Okay. But remember, any two states, when they're at equilibrium, whether the process is reversible or irreversible, the difference in any state function has to be the same, right? So we can then take that result that the entropy change, the differential entropy change, is always then greater than or equal to the heat flow divided by the temperature. And dq, remember that du is dw plus dq, right? So if I rearrange that expression, I know that du minus dw is dq. So I can take dq over t and replace that with du minus dw. Okay? And then I'm going to say that if I have only allow PdV work and materials transfer work, so phase transition or chemical reactions, I'm going to replace dW with those work terms, and I get this expression here. So this tells me that a differential change in the entropy is always greater than or equal to this expression over here. So this is a really important step here, right? This tells us that if we're looking at a process, then we can think about entropy as a natural function of U, V, and the number of moles of each species that's present. I can actually write out a more generic form of the differential equation. So let's say that we're at equilibrium. At equilibrium, this inequality just becomes an equal sign, because at equilibrium, we know that this becomes an equal sign. So I can write this expression here, and then I can see that what multiplies du, which is ds du, is just 1 over t. What multiplies dv, which is p over t, which is ds dv, is this expression here. And what multiplies dn becomes this expression here. And so what we have then is relationships between these coefficients and these partial derivatives of the entropy with respect to these natural variables. Right? Any questions about how I've done this little rearrangement here? So what's important is that these are all state functions on this side, and that's a state function over here. Okay? So at equilibrium, everything over here has got to be equal to that over there. Okay. So this brings us to a topic that's called thermodynamic potentials. Now, we learned in chapter 1 that we can talk about equilibrium in terms of a potential energy surface, right? Remember, when the potential energy surface goes down and it has a minimum, that's a point where if it's a minimum in a potential energy surface, that's a stable equilibrium point, right? It moves off to the left or the right, the force brings it back to that point. And if it was a maximum in potential energy, it was an unstable equilibrium point. It pushed it away from that point. So this idea of an equilibrium point can follow through into thermodynamics with this type of expression that I just showed you. So we have this expression here for the entropy, and we know that the system will proceed spontaneously towards equilibrium in a way that we will reach equilibrium when ds goes, the change in the entropy goes to 0. So when the entropy change goes to 0, that means we've reached equilibrium. But if it's not at equilibrium, then it will go spontaneously with the entropy change always positive. So when you reach equilibrium, it means that this equation tells you that the energy has stopped changing, the volume has stopped changing, and no more reactions are occurring. So du, dv, and dn are all equal to 0. That makes ds equal to 0. So that's the condition that we have in this expression for us coming to equilibrium. So entropy tells us when we're going to come to equilibrium. It's like this potential energy surface. It tells you where that stable equilibrium will be. And it's going to be where du, dv, and dn have stopped changing. Okay. So experimentally, you can go into the lab and you could say fix u and fix v, and then say, okay, I got a reaction that's happening in this vessel. I've isolated it, so volume is constant, energy is constant, and then I can use this expression here to predict which direction the reaction will go towards equilibrium, right? Because if I lock u and v, then I know that ds greater than 0 has to tell me the direction, which is the spontaneous direction for the reaction or the phase transition. So ds now tells us which way is spontaneous and which way is impossible. You see how that works there, okay? So if you're doing this, well, if you have a reactor and you're holding the volume constant and it's adiabatic, that's great. But what if you don't have a reactor where the volume is constant and the energy is constant, and you want to know which direction is spontaneous? Well, then this expression is not as helpful. But if you were under these conditions, then you could just simply look at the entropy change, and that would tell you which direction. Look at the initial and final entropies, and whichever one causes the entropy to increase, that's the direction that the reaction is going to go. Okay? But what if you're not at those conditions? Well, we can do some rearranging of this expression to try to get other types of conditions. And the simplest rearrangement, maybe not so useful, is just to rearrange it in terms of u. So I'm just going to flip everything around and rewrite it as du, and it comes out to look like this. Okay, that was just a very simple rearrangement. And what that tells us is that this process will proceed spontaneously if ds is, it will proceed spontaneously to make du go negative. So in other words, it's the opposite direction. So energy wants to minimize in the spontaneous direction, but until ds goes to 0, dv goes to 0, and dn goes to 0. Okay? So in this case, you see that the natural variables for u are s, v, and n. Okay? Whereas before, the natural variables in the previous case for entropy was u, v, and n. Now the natural variables are s, v, and n. So if we locked the entropy and locked the volume, then we know that any reaction that takes place, all you have to look at is u final and u initial and determine whether the reaction is going spontaneously one direction or the other. But this isn't a very helpful step forward, because now we have to have an isentropic process and a constant volume process, and who wants to design a reactor with its isentropic, right? So that's not so easy. You would like to have an open vessel, right, or a reactor where the temperature is constant. So that brings us to a new state function that we're going to redefine called the Helmholtz energy. If we define it in terms of other state functions, then it's obviously a state function. So if I say u minus ts is my new state function f, then if I can use that expression in those previous expressions, and I can find that df is going to be a natural function of t, v, and n. Now this is more useful. It tells us that a process will go spontaneously in the direction that causes f to decrease. So the delta f has to be negative for the process to occur spontaneously. And when it reaches equilibrium, then we'll be able to, this will be an equal sign, because these are all state functions on that side and on the other side. So when the temperature stops changing, the volume stops changing, and the reaction stops occurring, then we will reach equilibrium. And we can use f as a way to determine the direction that's spontaneous. So that means you have a reaction, and you have it in a constant volume reactor with a constant temperature, and you want to know which direction is going to be the spontaneous direction. You simply have to evaluate the free energy for the two different states to decide which direction, two equilibrium states, which direction is the direction that's the spontaneous direction. All right? So that makes this a much more valuable potential. We call this a thermodynamic potential, that will tell us where the equilibrium point is going to be and which direction will go towards equilibrium. Right? So entropy was useful, but you got to have a constant volume, constant energy, reactor to do that, so you don't want to use this. But if you have a constant temperature, constant volume reactor, then Helmholtz energy is the one you want to use. All right? Any questions about that? Yes?
So you can essentially use the Helmholtz energy and entropy depending on which kind of reactor you have to tell you where your process goes.
Exactly, exactly. So you look at your process and you think, what are the natural variables that I'm holding fixed? And then you look for a thermodynamic potential that will fulfill that need.
And then you can maximize however much you use it.
Then you can determine which direction is the entropy, which direction is the equilibrium direction. You know, the direction will go towards equilibrium, and then you can work out equilibrium constants and all these kind of other things. Yeah. But thermodynamics doesn't tell you about rates, right? Reaction rates is a different game. Thermodynamics only tells you about the equilibrium states. It doesn't tell you how long it takes to go from state A to state B.
It could instantaneously be years.
It could be years. It could be, you know, milliseconds. It just tells you what direction it's going to go. Okay. Now, another useful one, as you might imagine, you know, maybe we don't want to work at constant volume and temperature, but we want to work at constant pressure and temperature. So you can do the same thing. You can create another state function. Remember enthalpy, which was a good constant pressure state function. We take enthalpy minus T times the entropy, temperature times the entropy. We create a new state function called the Gibbs energy. And rearranging the previous expressions, we can come up with this expression where Gibbs energy is a natural function of temperature, pressure, and the number of moles of your substance. So if we're going to go spontaneously towards equilibrium, it requires delta G to be negative. And it means that you'll be at equilibrium when when dt goes to 0, dp goes to 0, and dn goes to 0, and all your reactions and phase transitions stop, right? So in the lab, it means that if you have an isothermal, isobaric reactor, then the spontaneity condition is delta G is going negative to determine the spontaneous direction for the chemical reaction or the phase transition. And that's probably maybe even more useful, particularly for the bench chemists, right, who are working in open beakers in the lab. So that one is probably the one that gets used over and over again. So I'll just kind of drive this one home a little bit more, that we define this delta G, which is just a state function in terms of delta H minus T delta S, all state functions over here. So if you're looking at a reaction, you can look at the delta H and the delta S for the reaction and the temperature where that reaction is occurring, and you can determine whether that reaction is going to go spontaneously one direction, say A to B, or spontaneously from B to A. And of course, you can have a bit of a battle between the terms that go into your delta G. So in other words, we have a delta H, which could be either exothermic, meaning the reaction gives off heat, or endothermic, the reaction takes in heat, and the entropy, whether the reaction increases causes an increase in entropy, or it causes a decrease in entropy. So you can see that if you have a positive delta H, so you have an endothermic reaction, and you have an entropy decrease with that reaction, then obviously positive minus T, which is always positive, times a negative means this whole thing is always going to be positive, which means that for a reaction, if this is, if this was delta H for A to B, and this is delta S for A to B, then that means that A to B is spontaneous for all temperatures. So in other words, delta G is, wait a minute, that's backwards. Did I write that backwards? Yes, I think I wrote that backwards. All right. Okay. Again, these are new slides. I'm just throwing these together at the last minute, so I expect there will be a few glitches here. So as long as delta G, so in other words, if the delta G is positive, then it's going to be spontaneous in the direction. So if I wrote this way, then this should be B to A, and because that means it's not going to go that way because that's the spontaneous direction. So the spontaneous direction is delta G of negative, right? So if A to B is positive, then B to A is the spontaneous direction. Okay, you got that? if A goes to B has a delta G that's positive, then this is not the spontaneous direction. So this is the impossible direction, right? And so that means that the direction that this goes is B to A is going to have delta G a negative, and that's going to be the spontaneous direction. All right. Okay, so little glitch in the notes there. Okay, so obviously I cut and paste and I did it the same here. So if your delta H is negative, so it's exothermic, all right, so you're already heading towards a negative delta G, and your delta S is positive, and there's a negative sign here, then obviously you're always going to get a negative delta G, and the process is always going to be spontaneous in the direction that has these values, all right? Now, so these two are always the same no matter what temperature you're at. So if you have a positive delta H and a negative delta S, then your delta G is always going to be positive at all temperatures. Same here. If you have a negative delta H and a positive delta S, then your delta G is always going to be negative at all temperatures. But if you have positive delta H and positive delta S, then it depends upon the temperature, because you see temperature is going to be amplifying the entropy term. So if temperature is high, then it's going to cause that process to have a negative delta G. If temperature is low, it's going to cause the process to have a positive delta G. So it's going to be positive at low temperatures and negative at high temperatures. Whereas if you have the opposite, if you have a negative delta S and a negative delta H, then this is going to be driving it towards spontaneous direction, but this is going to be driving it the other way. So this is going to cause an entropy increase. So you see here that if you go to lower temperatures, it's going to minimize the effect of that negative entropy change, and that's going to make the direction go spontaneous. So if it's going to be a positive value at high temperatures where this rules, and it's going to be a negative value at low temperature where this rules. All right? Yes?
So for this second row, is it supposed to be A to B spontaneous, or is it still?
I think, let me see. So this one is supposed to be B to A, and that one's supposed to be A to B, right? That's where I got it backwards. So if I'm saying that A to B is this, then that means that should have been B to A. So I think they're all backwards, but I got to go back and check it. So sorry about that. But anyway, this is sort of a review of something you see in high school and freshman chemistry too, the delta G's. I just wanted to sort of show it to you in that context here. All right, sorry about the confusion on the flips arrows. Any other questions on this one? Yeah.
So if your gauge is just 0, then it's just at an equilibrium point.
If the delta G is 0, you're at an equilibrium point. Yes. Okay. Now, just a little bit of some math tools that we'll be using. So when we're working with these state functions, it turns out that these are single valued functions. They have continuous derivatives. Then this df, whatever that state function is going to be an exact differential. So if we write it like this, which you've seen earlier, we can define this partial derivative as m and this partial derivative as n, so that if we take the second derivative of m and n with respect to the other variable, so this is the partial derivative with respect to x, that's the partial derivative with respect to y. So if we take m and take the partial derivative with respect to y, then it becomes the second derivative of f with respect to x and then y. And n, which is the derivative with respect to y, if we take a derivative of n with respect to x, it becomes the second derivative with respect to y and then x. But if it's a continuous single-valued function, then these two derivatives don't matter the order in which you take it, so this has to be equal to this. And so this gives us this rule here that we can relate anytime we have a state function where we've written it out in this form, then we can see that the partial derivative of m with respect to y at constant x is going to be equal to the partial derivative of m with respect to x at constant y. This will allow us to discover all kinds of what we call reciprocity relationships between the change of thermodynamic values using all of those thermodynamic potential equations that we saw earlier. Okay. So I have some problems that you guys can work through, but you can see, for example, if I have du is equal to t ds minus p dv, and I want to get the reciprocity relationships, then I just look at this and say, okay, I'm going to identify then that T is my M, and minus P is my N, and X is S, and Y is V, so I can go back to those relationships, make these identities, and I can see that I can derive this reciprocity relationship between the partial temperature with respect to volume at constant entropy is equal to the negative of pressure with respect to entropy at constant volume. All right? So that is how you would derive all these other relationships that we'll use when we're trying to work out thermodynamic relations for a particular situation. Okay, so I have some other problems for you to work through in the exercises like this. Okay, so now we come to the third law, and there's not much to say about this, but just to sort of let you know that it kind of follows from what we've learned before. So we learned from Clausius entropy that the entropy change is dq over T, and temperature is on the absolute scale, it's on the Kelvin scale. So if you actually get to absolute zero, then you can see that this is going to blow up, right? You're going to be dividing by 0 Kelvin. But in fact, actually, at 0 Kelvin, there's no motion. And so in order for heat to move between the system and surroundings, you have to be able to cause the molecules or atoms to move, right? And if there's no motion, then you can't have any heat flow too. So it looks like what's happening is that even though the temperature is going to 0, and that looks like that's going to explode, the dq is also going to be going to 0 as we get closer and closer to absolute 0. So we have what's called the third law statement, which is by Nernst, which says that in the limit that temperature goes to 0, the delta S will have to go to 0. Okay? So the entropy approaches a constant value as you approach absolute 0, and the change approaches 0. Okay? Now, there is another sort of more stricter version and a little bit more confusing. This one makes good sense, but Max Planck took it further, and this is sort of really in the context of statistical mechanics, so maybe come back to this later, but he said that you can actually define an absolute entropy, and you can define that if you had an absolutely perfect crystal where there was no disorder in the lattice, that in the limit that T goes to 0, you can say that the absolute entropy, not just the change in entropy, but the absolute entropy goes to 0. That's Planck's statement of the third law. And there's all kinds of exceptions to that, particularly with regard to residual entropy, it's called. So if you imagine that you're trying to cool something like carbon monoxide down to 0 Kelvin, as you get closer and closer, you expect it to order into this solid lattice. But as you try to do this, you have to cool it infinitely slow. And if you don't cool it infinitely slow, then what's going to happen is you're going to get trapped states. Maybe some of these carbon monoxides, because of their dipoles, they're going to be higher energy configurations because they're flipped the other direction. You can see that this is the lowest energy configuration, the minimum energy, but if some of them are stuck and they didn't get flipped to the minimum configuration, minimum energy configuration, and then there's no more thermal energy for them to actually get to that equilibrium state, then you get stuck into this state here, which is a non-equilibrium state. In other words, you know that equilibrium is this, but the temperature is too cold for things to rearrange to get into equilibrium, so you get stuck with something like this. So this is called residual entropy, but the challenge is that entropy really might not be defined like this like this for a non-equilibrium state. So I put it in quotes, residual entropy, but it's often talked about like this, as this is residual entropy. So with the idea that you can then have this absolute entropy, as Planck suggested, with this extra sort of fudge factor, which is that at 0 you might have some residual entropy, then you can take the entropy, calculate the entropy at any temperature by just knowing its original residual entropy at 0 Kelvin, and then integrating the expression for the heat capacity with respect to the differential of the log of T. That's our expression for entropy increase with temperature here, and then any phase transition along the way, when we go from solid to liquid to gas, we'll have this entropy increase. So you can take from absolute zero, you can find all the entropy changes in that material all the way up to the temperature in which you're working at, and then you have the absolute entropy at whatever temperature you're working at. But you have to take into account all the processes that lead up to wherever it is that you're working. Okay. So you can do this plot. You can basically just look at the heat flow as a function of temperature, and from that you can get the entropy at any temperature. At really low temperatures, it's very hard to do those measurements, so oftentimes people will go to a result that comes from statistical mechanics, which is that the heat capacity is just proportional to the temperature to the cubed root, and where A is some substance-specific constant, and you can use that to sort of help get you through the low temperature parts of this expression. So that gives you absolute third law entropies. So if you remember, we talked about enthalpy changes and getting around absolute enthalpies by using the delta H of formations, right? But when we talk about entropies, we can use actually absolute entropies. So if we're looking at a reaction to decide whether the reaction is spontaneous or not, and we're looking at delta H minus T delta S, then we can look at the delta H terms for the reaction in terms of the enthalpies of formation, the delta F's, the delta H of formations for the reactants and products. But for the entropy term, we can use the absolute entropies that you can look up and then combine these guys to get the delta G for the reaction and then determine whether it's going to be spontaneous or not. Okay. Again, this is probably something you remember, but just now we've sort of put it back into the context of all of this. Any questions here? I think that is the last slide on this. We're going on time. 12 o'clock. Any questions? Okay, so let's take a couple-minute break, stretch, whatever, and then I'm going to set up and start the next lecture.